All right, we're going to continue our dive in chapter 4 with talking about the structure of the atom, its properties, and what we call ions. All right, before we begin taking notes, go ahead and just close your eyes for me. Just close your eyes and kind of think about what you feel. Is there anything that you hear in the background? Any smells coming throughout your house or wherever you are? All of your sensations are because of atoms. Okay, kind of weird to think about, but all of your sensations, what you hear, what you feel, what you smell, what you can taste, is all because of atoms. Because matter is made of atoms, and atoms are everywhere. They're the foundation of our senses. They're the fundamental building blocks of everything you experience. Okay? Go ahead and open your eyes if you haven't done so already, and let's start talking about atoms. Atoms are the basic unit from which nature is built. They are the smallest identifiable unit of an element. Okay, so the properties of atoms are going to determine the properties of matter. So how atoms are structured and how they interact with each other is going to determine how everything else interacts with each other. It's like a big domino effect. In the previous chapter, we talked about the history of the atom and all the people, the philosophers, the scientists, the experimenters, who figured out what an atom is and what it's made of. And so now we've kind of settled on this nuclear theory of an atom, meaning that an atom is something that has a nucleus, a dense nucleus in the middle, and then there's a bunch of empty space on the outside, and we've got electrons on the outside, okay, in that empty space. So from the nuclear theory of the atom, we know that most of the atom's mass, right, comes from the protons and the neutrons, and all of its positive charge, because of the protons, are in the nucleus. So the nucleus is this very dense positive center. And most of the volume of the atom is actually empty space around it, okay, in which all of these electrons are moving. Remember, electrons are super tiny, and they have they have negative charge. Okay. So we also know from our nuclear theory of the atom that there are equal number of protons and electrons. So the number of protons equals the number of electrons in a neutral atom. They have to balance out so that an atom is electrically neutral in nature, and therefore not, wanting to, stick to something or react very easily to something else. Okay, so atoms are electrically neutral in nature because of that balance of protons and electrons. So let's dive into what we know about the nucleus. So inside of the nucleus, remember, we have protons and neutrons, and they have very similar masses. You can see there the masses of the protons and the neutrons. They are to the 10 to the negative 27th kilogram, which is amazingly tiny and light. So light that we actually give them their own unit. We call it the AMU, or the atomic mass unit. Just so that, anytime we're talking about the mass of a proton or a neutron individually, we don't have to say 1.67262 times 10 to the negative 27th kilograms. We can just say about 1 AMU. Okay. Now, electrons that are orbiting the outside of the nucleus have almost negligible mass. All right, so they are so super tiny. That would be 9.1 times 10 to the negative 31, okay, which is, 10,000 times smaller, okay, than the proton and the neutron. So they essentially have 0 AMU, okay, so When we say, electrons have no mass, it's technically not true, but they're so tiny, we basically don't count it. All right, and then in terms of charge, remember protons have a positive 1 charge and electrons have a negative 1 charge. And we have a balance of protons and electrons in an atom, so that that atom remains neutral. And neutrons have no charge. They are neutral. So they don't affect the charge at all of an atom. They just affect the mass. All right, and again, just to reiterate, super important to realize, okay, that matter is usually neutral because of the charges of the protons and electrons canceling out. All right, so when we talk about atoms, we need to talk about the number of protons, because the number of protons in the nucleus is going to identify what atom we're talking about. So for example, inside of these balloons, we have the helium atom. And if we looked and zoomed in at each of those helium atoms, we would find 2 protons and 2 neutrons. Okay, so every helium atom has 2 protons. If an atom has more or less than 2 protons, then it is not helium anymore. Okay, so the number of protons is the identity of the element. So if we found an atom with 13 protons, like this one, we would know that it has to be aluminum, because aluminum always has 13 protons. So again, the number of protons identifies what atom, what particular element the atom is. All right. This number of protons is what we call the atomic number, symbolized by the letter Z. Not sure why, but we call that the atomic number. So if a question asks, hey, what is the atomic number of carbon, right? You're just going to tell me how many protons carbon has. All right, so how do you figure out what the atomic number of an element is? Well, we have to reference our periodic table, right? So our periodic table is going to look something like this. Now, the inside of the boxes might be rearranged differently or whatnot, but it's going to have this basic structure here with the columns and the rows, and all of the elements are going to be in their exact column and row. All right, and each of these boxes represents an element that is found in nature, and this box is going to tell us about the atom of the element. So we can see here that there's a letter associated with each element. We call it the chemical symbol. That letter is basically a shorthand, okay, for the actual chemical. For S, for example, is the chemical symbol for sulfur, right? Some of these chemical symbols don't have anything to do with their English name. So like Na is sodium, okay, but Na comes from its German root natrium, right? So similar to potassium is K, but potassium doesn't start with K, right? Iron is Fe because it comes from the Latin root of ferrous. Cu for copper because of cuprous, right? So a bunch of elements may not have the symbol that is associated with their English name, right? Other elements are named after countries. Like Ge is germanium, named after Germany. And we have polonium, named after Poland, right? We have americanium down there, named for America. And then we've got other elements that are named after people, like Es, number 99, Einsteinium. Number 101 is named after Mendeleev, the father of the periodic table. We have 96, Cm is curium, named after Madame Curie, who was a pioneer in discovering radioactive elements and working with their properties. So the periodic table is kind of a hodgepodge of science from around the world, all put together to figure out, how nature works. So when we take a look at the symbol box, all right, we've got the chemical symbol in the middle, and then we usually have a number on top. The whole number there is going to be our atomic number, our Z number, our number of protons. Okay, So the atomic number equals the number of protons, which, remember, has to equal the number of electrons as well in a neutral atom. So sulfur, for example, is number 16, so we know that he has 16 protons, and he therefore has to have 16 electrons. And then on the bottom, we have a decimal number, and that decimal number is what we call the mass number, and it's actually an average atomic mass. It's a decimal because not every atom of an element has the same number of neutrons. Okay, so neutrons can vary. We call those isotopes. And so if we added up and averaged the mass of all of the different isotopes of an element, we'd come up with a decimal number. So that's why we've got the decimal there for the average atomic mass. All right, so that's all the information that our periodic table tells us. All right, like I mentioned before, Mendeleev is the founder or father of the periodic table. So in 1869, he kind of thought up and started working with trying to organize the known elements on Earth at that time in the late 1800s. He was a Russian scientist. He actually wanted to go to med school, but was not accepted to med school. So he went to university and studied chemistry instead, and fell in love with the elements, and basically kind of obsessed about them and tried to figure out, as much as he could. And from all of the features and properties that he knew about the elements at his time, he was able to put them into this first rudimentary periodic table that we see here. So this is a kind of a rendition of his. So you can see that he still has groups, right? In fact, he still has 8 main columns of the periodic table, just like ours has 8 main columns. We do have the little transition metals in between. And he's got, rows as well. Okay. And so we've taken his initial jab at the periodic table and kind of refined it over the years. And we've refined it according to what we call periodic law, where we've basically kind of discovered that certain elements have similar properties that occur in regular patterns. And so we can put those repeated patterns on the periodic table. And so Mendeleev was the first to identify this and discover this, and this actually allowed him to predict properties of yet discovered elements. So for example, like anytime you see this dash, he knew exactly what the properties were for all of those dash elements, okay? But they were yet to be discovered. So it's kind of cool. So Mendeleev's periodic table eventually turned into what we know today as our periodic table of elements. So now it looks like this. Again, it still is organized around periodic law, where we have certain, everybody in the certain columns down the groups. Okay, at least the main groups have similar properties and perform similar chemical reactions. All right, and the rows as well have different properties and trends and patterns that we're going to see emerge as we study this periodic table. All right, so one of the patterns that emerges is that more than half, okay, about 2/3 of the periodic table are made up of metal type atoms. So everything in green you see there is a metal type atom, and metals are good conductors of heat and electricity. They're malleable, ductile, shiny, and most importantly in chemistry, they are going to lose electrons when they undergo chemical reactions. Okay, so metals lose electrons. We need to remember that. Put that in your brain. Okay, and you can see that all of the metals are on the left-hand side of the periodic table. We do have one poser. Okay, so caution to this poser right here. Little caution symbols. All right, hydrogen is on the metal side, but he is not a metal. Hydrogen is the lightest and first element on the periodic table, so there's no way it could be a metal. He's a gas, but he acts like metals a lot of the time. So he's kind of a poser, I call him. So please be careful in identifying hydrogen as a gas and not a metal. All right, nonmetals we're going to see in blue on the right-hand side of the periodic table. These guys have varying properties. They're poor conductors of heat and electricity. Some of them are gases, some of them are solids, some of them are powdery, some of them are brittle rocks. It just depends, okay? So nonmetals have much more varied properties than metals. But again, the most important to remember is nonmetals always gain electrons when they undergo chemical changes. So in a chemical reaction, a nonmetal is going to gain electrons from the metals, right? So metals lose, nonmetals gain. Got to remember that. All right. And then last but not least, right there in the middle, we honestly don't focus on them too much. We've got the purple ones there, starting with boron, silicon, germanium, astatine, antimony, tellurium, polonium, and sorry, that was arsenic, polonium, astatine. Okay, these guys are metalloids. They're kind of on the staircase of they make a staircase in between the metals and the nonmetals. These guys, like nonmetals, have mixed properties. They're semiconductors, so they have intermediate electrical conductivity that can be changed and controlled. So they're not superconductors of heat and electricity like metals are, but you can actually be able to control their conductivity of heat and electricity, which makes them very useful in computing. In fact, most of the motherboards are made from silicon, which is a metalloid right there in the middle there. All right, so again, we don't really focus on them as metalloids, but they do exist, and they're kind of like this blurry line between metals and nonmetals. They have some properties of metals and some properties of nonmetals. All right, so we can see on the periodic table we have kind of two main groups. So we've got the tall columns on the very left and the very right. Okay, we call those main group elements. And then we have the middle section, which are transition elements. Okay, so the main group elements, the main 1 through 8, 1A, 2A, 3A, 4A, 5A, 6A, 7A on the periodic table. So we call main group elements. Their properties are predictable based on their position on the periodic table. These are the ones that Mendeleev had no problem saying, yep, these guys behave exactly the same, so I'm going to put them in the same column. All right. So everybody in group 1A behaves the same way when we're chemically, we're talking, when they react. Okay, and we'll see why in a little bit here. But they have very predictable properties. The transition metals, on the other hand, okay, are less predictable. And again, we'll see why. It has to do with the number of valence electrons and how many they like to, give up, depending on who they are reacting with. Okay, so these transition metals, I often refer to them as pains in the butt because they kind of mess things up. They don't go with the patterns, and they kind of screw things up in terms of, once you've, figured out, oh, it works like this, and you're like, nope, not want to hit the transition metals. All right, so just know that the transition metals are in that middle, and they're going to mess up our awesome, predictable properties of elements. All right, so when we look at the periodic table, there's different names for the different sections, like we said, and there's also names for the different columns. So these are what we call group or family names. These groups or families, just like your family at home, okay, have similar properties. So maybe, in your family, freckles run, genetically through your family, and that's a similar property. So, you guys would all be in one column, right? Maybe dark hair runs in your family. So that's a similar property between all of you, and that, makes you, this group that is similar. So it's the same kind of thing here with elements. All right, all of the ones in group 1A all have similar properties, so they're all called alkali metals. Right, group 2A all have similar properties, so these guys are alkali earth metals. The middle there, remember we called transition metals because they screw things up. Now, 3 through 6 don't have specific names, because if you see, as you go down, you go from nonmetals to metals, nonmetals to metals, nonmetals to metals, nonmetals to metals, right? Because remember, it's this staircase right here that divides the metals on the left with the nonmetals on the right. So 3 through 6 those groups don't have similar properties, because some of them are metals and some of them are nonmetals. But as soon as we get to group 7 again, they're all nonmetals, and so they all have similar properties. We call those halogens. And then last but not least, the tall one on the very end is the noble gases. All right, so now it's time to grab your periodic table, and we're going to classify each element as a metal, nonmetal, or metalloid. So go ahead and find barium on your periodic table. You may need to, if you can't find it right away, because you're not quite familiar with the periodic table yet and where all the elements are, go ahead and pause. You can pause the video at any time that you need. Find it, and then classify it, and then we'll go over the answers together. Okay, so barium is on the lower left-hand side of the periodic table. He is a metal. He's on the metal side. Iodine. Go ahead and find iodine. Should have found iodine on the right-hand side. Group 7. Group 7 is the halogens. These guys are non-metals. All right, the next one is nearby oxygen. So I gave you a little hint there where you can find oxygen. He's in group 6A. Again, he's on the right-hand side of that staircase on the non-metal side. Plus, oxygen, it's what we breathe in, right? Every time we inhale, we breathe in oxygen, so it must be a non-metal, right? If it was a metal, we'd, be breathing in solid chunks of shiny stuff, and that's not what we breathe in, okay? So there are times when if you forget, you're like, oh my gosh, is it the metal or non-metal side? Think oxygen, we breathe that in. Must be a non-metal. All right, tellurium. Go ahead and find tellurium. He's just down from oxygen, but he's in that metalloid section. He's right there on this staircase, and the ones that kind of hug the staircase, all of them except aluminum. Aluminum's a legit metal, all right, but all the other ones that hug that staircase are going to be metalloids. All right, now for this next section, we're going to figure out what family name or group they belong to. So the family name or group was like the transition metals or the alkali metals. All right, so magnesium. Go ahead and find magnesium. Should have found him in group 2A. Group 2A is called the alkaline earth metals. So alkaline earth metals, magnesium, calcium, beryllium, all those guys. All right, nitrogen. Go ahead and find nitrogen. He has no name, right? No special name. Remember, he's in group 5A, and group 5A are nonmetals at the top, and as you go down the group, it turns into metals. So no name for them. Potassium, though. Go and find potassium. He's on that left-hand side. In fact, he's in column 1. Column 1 are the alkali metals. If you ever heard of or recognize the word alkali, like in alkali batteries, okay, some of those metals are used in batteries. Okay, because they give up their electrons very easily. So they're going to be able to allow electricity to flow through them, okay, much easier than nonmetals. All right, last but not least, bromine. Go ahead and find bromine. He's on that right-hand side in group number 7. And remember, group number 7 are called the halogens. All right, good. So, hopefully that was easy for you and a review of regular chem. If not, please make sure you spend some time getting those back into your memory banks. All right, because we don't waste any time in here in dual chem, we're going to jump right from learning about the atoms and their structure, number of protons, electrons, and how to find them on the periodic table, right into ions, which is now, so we made a big deal about the number of protons and electrons being equal in an atom. That way they're neutral. Now we're going to talk about atoms that lose or gain electrons. So now we don't have an equal number of protons and electrons. These guys are called ions. All right, so ions are atoms that lose or gain, okay, electrons to form charged particles, right? So there is either going to be negative charges or positive charges in these because there's no balance between protons and electrons anymore, right? So we can say the number of protons is not equal to the number of electrons in ions. Okay, so the charge is going to depend on how many electrons are gained or lost. We're going to find out that some elements lose 1 electron, some elements lose 2, some lose 3, right? Some gain 3, some gain 2, some gain 1. All right, but don't worry, they all have patterns on the periodic table. So it's not like you have to memorize who, loses how many, because they're all, for the most part, for the main groups, are going to be a pattern. All right, but in general, to figure out the ion charge, what we're going to do is we're going to take the number of protons and we're going to subtract the number of electrons. When you do that, if you get a positive charge, okay, that means that it lost electrons and is become what we call a cation. Okay, cations are positive ions. It's just this fancy special name for positive ions. One way you can remember that is cats have paws, like positive, okay, or you can think of that plus sign in the middle. I'm sorry, the T in the middle as a plus sign for positive. Okay, now if you subtract the number of protons minus the number of electrons and you get a negative number, that means you had more electrons in the atom, and electrons are negative. So we're going to end up with anions or negative ions. In fact, anion means a negative ion. There you go. All right, so one thing that we do need to make sure that we understand is that ions behave very differently than atoms. They do. It's weird. Okay, just think about sodium and chlorine, right? Sodium as a neutral atom is a metal, like a legit, like look outside and look at your car, metal, okay? But as soon as sodium loses a electron, he doesn't have those metallic properties anymore. Okay, it's not shiny, it's not hard or anything like that. His ion behaves and looks very differently. Okay, chlorine in nature, the neutral chlorine atom is a gas. Chlorine ion behaves much differently than that. All right, and when we get sodium ion and chlorine ion to hook up together, now it's kind of mind-blowing. You take a metal and you take a gas, you mix them together, and you get salt, right? That you eat on your French fries. It's like, what? So ions behave very differently from the atoms in which they come from. Got to remember that. All right, so let's practice this and let's figure out what charge each of these ions has. Okay, so remember we're going to do the charge equals the number of protons minus the number of electrons. So for the first one, we have magnesium. Magnesium has 12 protons, and this particular atom has 10 electrons. So 12 minus 10 is positive 2, right? So this magnesium ion is a charge of plus 2. The second one, sulfur. Sulfur has 16 protons. And in this particular ion, he has 18 electrons. So 16 minus 18 is negative 2. So the charge on this one is negative 2. Now he's got 2 extra electrons than protons. So he's a negative charge. All right, last but not least, iron is number 26 on the periodic table. So that means he has 26 protons. And in this particular ion of it, he has 23 electrons. So 26 minus 23 is a positive 3. So that means he has 3 more protons than electrons. So he lost 3 electrons here and has become a positive charge. Okay, so that's how we're going to figure out the charges. The number of protons minus the number of electrons. All right, so hopefully you noticed on your periodic table, you've got sections with A's and sections with B's. So for example, the first 2 columns are A, the next 10 columns have B behind their numbers, and then the last 6 columns all have A again. Okay, remember the A columns, those big tall columns, are what we call the main group elements. Okay, and then the shorter ones, okay, are the B group or the transition metals, transition group. Okay, so it's important to, again, have this distinction because remember the main group elements have predictable properties and the transition ones don't. And one of the predictable properties that the main group elements have are the number of valence electrons. Okay, the number of valence electrons is the electrons on the outermost ring around the nucleus. So when we talk about atomic structure coming up, we're going to talk about how electrons are in shells around the nucleus, like little orbits or rings around the nucleus. And so the farthest one from the nucleus is what we call the valence electron. All right, and the valence electron is that A number. So group 1A has 1 valence electron. Everybody in group 2A has 2 valence electrons. Now it doesn't work for the B's, okay, because I'll tell you right now, some of those elements in the transition metals have one number of valence electrons and some have varying numbers of valence electrons. So that rule doesn't work. That's, what I mentioned before about them screwing up our rules. But as soon as we get over to group 3A, going along with our pattern, has 3 valence electrons. 4A, 4 valence electrons. 5A has 5 valence electrons, so on and so forth. All the way over to group 8A. All of them have 8 valence electrons except for helium. So please make sure you have that exception. Helium, I call the little baby of the noble gases. He's a little guy. He can't hold 8 valence electrons. We'll see why when we talk about atomic structure. But helium only has 2 valence electrons. All the rest of them have 8 valence electrons, but helium's a little guy and can only hold 2. Okay. All right, so that is one of the first patterns that we're going to talk about on the periodic table here. All right, so on the last slide, the very last thing I mentioned there in bold is that all of these main group elements are going to become ions that have the same number of valence electrons as their nearest noble gas. Okay, so what that means is, let's take a look at group 7, right? Group 7 has 7 valence electrons. The nearest noble gas to them is group 8. So in order to get 8 valence electrons, everybody in group 7 needs to gain 1 valence electron, right? So 7 plus 1 is 8. Does that make sense? So everybody in group 7 is going to gain 1 valence electron, so they have the same number as the noble gas nearest them, right? So the same thing's going to happen with group 6. Group 6 all have 6 valence electrons, and they are all going to gain 2 to get to their nearest noble gas, okay? So they have to gain 2 valence electrons, okay? Everybody in group 5 has 5 valence electrons, right? And again, their nearest noble gas is this way, right? So we're going to gain 3 valence electrons when, in order to get as many valence electrons as their nearest noble gas. So bottom line, remember we already talked about non-metals gain, right, electrons to have the same number as the nearest noble gas. So just look right across the row from your non-metal to the very end of the column, right? The very, very end of the row, the last column in the row, and that's how many valence electrons he needs. Okay, so he's going to gain as many to get to the nearest noble gas. Now, metals, on the other hand, metals are going to go backwards on the periodic table. Okay, so lithium is going to lose his electron to become, or not become, to have the same number of valence electrons as helium, right? Or potassium is going to lose its electrons to have the same number of valence electrons as argon. Okay, so metals, like we already mentioned before, it's one of the properties of metals. Metals lose valence electrons in order to have the same number as, we're going to say, the noble gas before them, right, on the periodic table. So going backwards. Does that make sense? If it doesn't, please make sure you ask. So on this slide, what we're going to be doing is based on their position on the periodic table, we're going to figure out what ions these elements make. So like, do they make +2 or -3, right? So barium, for example, down here, he's got 2 valence electrons. He's a metal, right? So he's not going to, gain however many that is, okay, to be like right on there, okay? Can't happen, remember, because metals have to lose. So barium is going to lose not just 1, because if he loses 1, now he's like cesium. He's not a noble gas. He's going to lose 2 valence electrons so that he has the same number as xenon. So when we lose, we become a positive charge, right? So barium loses 2 to become like xenon, right? So barium has 56 protons, and if he has the same number like this noble gas, that's 54. So 56 minus 54 is a +2, so he must have lost 2, becoming a +2 ion. You see how that works? Let's do another one together. Iodine. Iodine is on the right-hand side. He's a nonmetal. Remember, nonmetals always gain electrons, right? So he's got 7 valence electrons. He only needs 1 more to be like the noble gas. So he's going to gain an electron. Remember, gaining electrons mean you become negative, right? If we do that math, iodine is 55 protons, and if now he has the same number of electrons as xenon, that's 56. So 55 minus 56 is -1. Okay, let's do one more together, and then I'll have you guys pause it. You can do the other 3 on your own. So oxygen's in group 6A. He has 6 valence electrons. He's a non-metal. Non-metals must gain. So how many more does he need to be like noble gas nearest him? Well, his nearest noble gas is neon. And neon has 8 electrons. So oxygen needs to gain 2 more. Right? So if you gain 2, that means you get a negative 2 charge. Right? So oxygen he has 8 protons, and if he in the end needs to have the same number of electrons as his noble gas, that's 8. So I'm sorry, that's 10, right? So 8 protons minus 10 electrons is negative 2. So he's a negative 2 charge. Okay? So go ahead and pause and do the last 3 on your own. Okay? Hydrogen is a tricky one. I'll tell you right now, remember, he's a non-metal, but in this case, he's going to act like a metal. Okay, so I'm just give you that hint. So go ahead and pause, and then when you're done, unpause, and then we'll go over the answers. All right, so potassium is in group 1A, 1 valence electron. He's going to lose because he's a metal, so it's going to be a positive 1. Phosphorus, so potassium is here. Phosphorus over here on the non-metal side, Phosphorus on the non-metal side. Non-metals always gain. In order to have the same number of electrons as the noble gas, right, he needs to gain 3. So that means he's going to have a negative 3 charge. And then hydrogen, I said earlier, is a non-metal on the metal side, right? In this case, he's acting like a metal. He's going to lose his valence electron. And when he loses his valence electron, it becomes a positive 1. Now, there's no noble gas before hydrogen, because hydrogen is where it all begins. So when hydrogen loses his electron, he's legit just a proton. That's all he is. He's a lonely little proton in the world. All right. No electron to buddy him up. All right. So that's how ions work. So hopefully you guys understand the organization of the periodic table, how to find the number of valence electrons, and then how to figure out if they're going to lose or gain valence electrons and how many. All right, so if you don't understand, go back to the spot and kind of rewind and see if you can understand by watching it another time. Okay, otherwise go ahead and ask me in class.